Today we're going to look at another type of factoring. It's probably the most complex type of factoring. This is factoring trinomials when the leading coefficient is greater than 1. Often we'll write out trinomials as x squared, and then there's an x term, and then there's a number. And often in mathematics we label these terms. So the first term, often we'll give it as ax squared plus bx plus c. So when I say that we're looking for trinomials where the leading coefficient is greater than 1, we're talking here about a not being 1. So a being greater than 1. We're actually going to start, though, by reviewing what happens if a equals 1. For example, the polynomial on the left, what would that rectangle be written as a full polynomial? It would be 1x squared plus 5x plus 6. Now you can factor this polynomial by looking at the width and the length, because we have a model. We've also learned the steps. And the steps involve a pattern where we notice that the factors of the last term also have to have a sum or add up to the middle term. So you could just, using the steps, look for the factors of 6. The factors of 6 are 1 and 6, or 2 and 3, and then find the pair that have a sum of 5. So our factors will be x plus 2 and x plus 3. Of course, we can confirm this by distributing, or we could use the model. We can look for the length, which would be x plus 3, and we can look at the width, which is x plus 2. So that's how we learned how to factor trinomials when there's 1x squared. But take a look at the polynomial now on the right. This polynomial has a leading coefficient greater than 1, and in fact, specifically, there are 2 x squareds. Let's finish by writing out what you think the rest of the polynomial is. 9x plus 4. And pretty quickly we can see that we need a new method. Our previous method was to look for the factors of 4. But that no longer will work because there are no factors of 4 that add up to 9. But this polynomial factors, and we know it factors because of the rectangle and the area model. In fact, we could find the factors. Probably do that in a later slide. But it does factor, but not using the method that we previously learned. So let's answer our question. Can you use the steps for the 1x squared trinomials? And the answer is no. We need a new method. Let's take a look now at what we've learned, which is that a polynomial that factors can be formed into a rectangle. The polynomial itself would be all of the tiles, and in this case the polynomial is 3x squared plus 8x plus 4. Again, we can't use the previous method where we're looking at the factors of 4, but we can use the area model. And so specifically we're going to look at the width, which is x plus 2, and the length, which is 3x plus 2. How do we check factoring questions? Well, the opposite, of course, of division is multiplication, so we can just quickly check through distributive property. We get 3x squared, 2x, 6x, plus 4. We have like terms here, and so our final solution is in fact what we started with. which confirms that we must have factored this trinomial properly. Again, notice we can't use the previous method of working with trinomials, but we can still use the area model. Before we get into the steps involved in factoring trinomials with a leading coefficient greater than 1, I want you to notice a pattern when we multiply binomials. So I'm talking about the distributive property here, which of course can be used to do mental math, in this case 12 times 13. We can use the distributive property to come up with the answer in our head. And all of the products here are pretty easy to work with. So the sum of these four terms, which is 156, is in fact the product of 12 times 13. But the reason I'm showing you this pattern is for a different effect, and that is to notice when you have your terms written out that the product of the first and the final term is equal to the product of the middle terms. So we have 100 times 6, or 600, equals 30 times 20, or 600. Let's see if that works for subtraction. So using the distributive property, we have 100 minus 50 plus 50 minus 25. Of course, these are opposite, so they cancel, and you end up with 75 as the answer. So 15 times 5 is 75. But again, look for the pattern of the first and last terms product, negative 2,500, and the inside terms product, also negative 2,500. We can demonstrate this algebraically. Again, doing the distributive property, we get four terms, and now if we look at the product of the first and last term, which would be A, B, C, D, and the product of the middle terms, we see they're the same. So we can complete this sentence. Notice that the product of the first and last terms equal the product of the middle terms. This is just the background and the reason why one of our first steps when we do decomposition is to multiply the first and last terms together. So, before we finalize all the steps to decomposition or for factoring trinomials with a leading coefficient greater than 1, we're going to use a technique called factor by grouping. And it basically involves taking our trinomial and dividing it. Let's turn that off. Into two parts. So what we're going to end up with when we do decomposition is we're going to end up with two separate polynomials. So let's write out what these two polynomials are. The one on the left is 2x squared plus 1x. And now the polynomial on the right is 8x plus 4. Now you have to remember that the original polynomial, in other words these two pieces combined, was 2x squared plus 9x plus 4. And we're going to show how decomposing it, breaking it into two parts, can lead to the factors. We end up with two rectangles, and each rectangle can be factored on its own. We call this, when we factor it into groups, factor by grouping. So I'm going to show you what factor by grouping looks like. Factor by grouping is, again, when we have, in this case, four terms, we split it into two groups of two, and we factor each group separately. the first group, we're going to use a technique which we've learned, which is called greatest common factor. And you'll notice that the first group has a common factor of x. If we divide it out, we get x times 2x plus 1. You'll notice the second half of this question was also a greatest common factor. In this case, though, the greatest common factor